Hello everyone, I am Dr.S.Shanmuga, working as an assistant professor at PG and Research Department of Physics, Sita Lakshmi Ramaswamy College, Tiruchirappalli. In today's session, we are going to see about Einstein AB coefficient. This Einstein AB coefficient is going to relate the stimulated emission and stimulated absorption process. So before going into the lecture, we'll see what is laser. So we know that the lasers are nothing but light amplification stimulated emission of radiation, and the laser lights are monochromatic, coherent, intense, and they hardly diverge. Whereas in this case of sunlight, it consists of different wavelength from gamma ray to the radio waves. And similarly, the LED lights are monochromatic in nature, but they have different phase and amplitude. See here the phase difference and amplitude difference that are emitted by the LED light. Whereas in this case of laser, from the source to the destination, the wavelength are same. I mean, they are monochromatic and they have same phase and same amplitude. And this diagram is going to tell you the difference between the laser light and the ordinary light. The monochromatic laser light is monochromatic, whereas the ordinary lights are having a different wavelength. They called as polychromatic light, and they are highly directional, whereas in this case of ordinary light, the photons are emitted in different directions and they are not coherent. They are not coherent, whereas the laser light are coherent in nature. So how this laser action is produced? In order to explain this phenomena, let us consider a two-level lasing system which is having one lower state and upper level. We know that the lower state is the stable state and the upper level is an unstable state. So when we have in the stable state and the thermal equilibrium, the photons are at the ground state or the lower state. This photons will go to the upper level by means of some induced action. So this induced action is called as stimulated absorption, because the incoming radiation will be absorbed by the photons at the ground state, and by absorbing the energy, it will make the transition from the lower level to the upper level, and this transition is called as a stimulated absorption. And this stimulated absorption is possible only when the incident radiation energy, say h nu, is of the order of the energy gap between the upper level and the lower level. Otherwise this stimulated absorption won't happen. And what will happen if the photons are at the excited state? We know that the excited state are highly unstable. So either by means of spontaneous emission or by the stimulated emission, it will come back towards ground state. So in this case of spontaneous emission, the photons are emitted at the different directions and they are not coherent in nature. This is what happening in our ordinary light sources and in the sun. So how the stimulated emission is happening? So again, by means of some external input, the stimulated emission is happening, and only in the stimulated emission we can expect the coherent radiation. Right? And is it this alone is enough to produce the laser? No, it is not enough. So we need to produce the population inversion. What is population inversion? It is nothing but the number of photons in the excited state should be greater than the number of photons at the ground state. So again, by means of stimulated absorption only, we can bring the photons to the excited state. So we know that the excited levels are having very less lifetime, that is 10 raised to minus 6 seconds. So while transferring the photons to the excited state, then automatically by spontaneous emission, again it will come back to this ground state. So we are spending lots and lots of energy to move the photons from ground state to the excited state, but without any means it is coming back to the ground state. So population inversion we have created, but what is the lifetime? It is not enough to produce the lasing action. So what the scientist has made by means of doping on by adding the impurities, they have produced the state called a metastable state, where the lifetime is 10 raised to minus 3 seconds. So they are transferring photons from the ground state to the excited state by stimulated absorption, and then by spontaneous emission, it is the photons at the excited states are coming to this metastable state. So they are staying there for 10 raised to minus 3 seconds. Then obviously when compared to the number of atoms in the ground state, now we have more number of photons at the metastable state. Now again, by this induced or the stimulated emission, the photons are emitted to the ground state, and this emission is called as stimulated emission, and this is how the laser lights are produced. Okay, so now we'll see what is Einstein AB coefficient. This Einstein AB coefficient will be relating the spontaneous emission and the stimulated absorption or the stimulated emission, and it was first given by Einstein around 1917 in order to explain the Planck's radiation law. Here in this Einstein AB coefficient, the coefficient A is related to the spontaneous process, whereas the coefficient B is related to stimulated process. We know that the spontaneous absorption is not possible in our thermal equilibrium, whereas the stimulated emission and stimulated absorptions are possible. Alright, so now in order to explain this Einstein AB coefficient, now let's consider that we have two-level laser system. The ground state is given by I and the excited state is J, and mu is the frequency of our incident radiation. And the energy h nu is of the order of excited energy of the incident radiation is of the order of the distance between the excited state and the ground state. So we have photons at the ground state at the thermal equilibrium, and this process is happening at thermal equilibrium T, and U nu is the density of incident radiation. So what will happen if an incident energy h nu is falling in this two-level laser system? It induces the absorption process, or we are calling this process as a stimulated absorption process is happening. So this makes the photons to jump from the ground state to the excited state. So what are all the things that has been dependent on? So now let's consider the transition is given by Nj. It means the photons are jumping from N to J. So it is given by Nj. The energy of the ground state is given by Ei, and the energy of the excited state is Ej. And similarly, Ni is the number of atoms corresponding to our ground state, and Nj is the number of atoms in the excited state. So if we have more number of atoms in our ground state, then obviously the transition will also, the probability of transition is also higher. So the probability of Nij, it is directly proportional to the number of atoms what we are having, and similarly it will increase if I have more photon radiation, or the density of radiation is high, we can expect more number of absorption will takes place. So in order to make this one as a equation, we have to introduce a constant, and as it is a stimulated process, we need to use B, and the transition is happening from I to J, so the coefficient is initiated with Bij, Ni and U nu. So this is the probability of transition for a stimulated absorption process. Now the atoms are at the excited state, right? So from the excited state, the atoms has to come back towards original state or the ground state in order to gain the stability. So it can happen in both the ways. One is the spontaneous process, and the another one is by means of incident radiation, and this one is called as a stimulated process. The spontaneous process should be initiated with A, and stimulated process should be B. Alright. So now let's consider the probability of transition from I to J, because it is happening from J to I. So the coefficient of probability is given by Nji, and similarly in this case of a spontaneous process, if we have more number of atoms in our excited state, then we'll have more transition. So it is directly proportional to the number of atoms in the excited state. And then it is not dependent on any incident radiation. So it is Nij is equal to Aj Ji and Nj. And in this case of stimulated emission, as seen our stimulated absorption process, Nj is directly proportional to the number of atoms in the excited state, and it is directly proportional to the incident radiation. So we can write Nj is equal to what? Bji here, because from J to I the transition is happening. Alright, so it is Bji Nj then U nu. And what about the Nji, and we know that Nij is given by what? Bij U nu, and then the number of atoms in the ground state. So we have three equations now, and we know that the process is happening at the thermal equilibrium. So at the thermal equilibrium, number of photons or the probability of upward transition is equal to the probability of downward transition. The upward transition is nothing but our absorption, and the downward transition is nothing but our emission. And we have two equations for our emission, so we can write Nji is equal to Aji Nj plus Bji Nj U nu, or we can write Nj Aji plus Bji U nu. So this is the probability of transition for the downward, and this is the probability for our upward transition. So at the thermal equilibrium, both are same. So what we are going to do is we are just going to equate them. Bij U nu Ni equal to Nj Aji plus Bji U nu. So now what we are going to do is we are going to solve this equation for the density of incident radiation. That means we are going to solve this equation for U nu. So in order to make this equation simpler, what we are going to do is we are just going to divide this equation by Bji. So if I divide this equation by Bji, then it becomes Bij Bji, then U nu Ni, and let's bring this Nj also here. Then I'll be having Aji by Bji plus U nu. Alright, so let's solve this equation for U nu. So if we solve this equation for U nu, to make this simpler, I'm just doing it here. U nu equal to what? Aji Bji by Ni by Nj, Bij by Bji, then minus 1. This is what the equation. So now again I'll be writing this equation again. Aji by Bij by Ni by Nj, Bij by Bji minus 1. And we know this Bij is meant the coefficient for the upward transition, and this is for downward transition, and at the thermal equilibrium both are same. So Bij is equal to Bji. So we can neglect this term, and we have this U nu is equal to Aji by Bj. So we can write Aji by Bij by Ni by Nj minus 1. And we know that Ni is nothing but the number of atoms at the excited state. So we can write the number of at thermal equilibrium, it is given by exponential minus Ei by Kt, where A is the energy of the photons in the ground state, and similarly Nj is given by C into exponential minus Ej by Kt. So we need to calculate what is Ni by Nj. If we calculate, then we'll be getting exponential Ej minus Ei by Kt. We know this Ej minus Ei nothing but the energy gap between the excited state and the ground state, and we know the incident energy is having the same energy of this energy gap. So we can write this one as e power h nu by Kt. So now I can write U nu is nothing but Aji by Bij by exponential h nu by kt minus 1. And this equation is analogous to our Planck's radiation law, where the incident radiation density or the density of incident radiation is given by 8 pi h nu cube by c cube 1 by e power h nu by kt minus 1. So by equating these two equations, we'll get Aij by Bij equal to 8 pi h nu cube by c cube. So what is this Aj? This is nothing but the spontaneous emission. So the spontaneous emission to the stimulated emission or the absorption, because we know that Bij is equal to Bji, they are equal to 8 pi h nu cube by c cube. And the Einstein proved that in order to calculate Aj or Bji or Bij, we need to calculate any one of this coefficient. So by calculating one of this coefficient, easily we can calculate the rest of the two coefficient, and they prove that the ratio between the spontaneous emission to the stimulated emission is directly proportional to the cube root of the incident radiation frequency. Thank you for listening. Thank you.